This is the final exam review for Math 1050, Spring 2026. Question 1, this is from Unit 1. We're finding the inverse. So remember, that's what this symbol means, find the inverse of these following functions. So two major steps to finding the inverse of a function is first, switch the place of x and y, and then second, to solve for y. So part A, first thing I'm going to do is switch the place here of x and y. So I'm going to say x is equal to y squared minus 5. And remember, this is how we did it in class. We just replaced f of x with y. So when I say switch the place of x and y, f of x is y. So there's step 1. Step 2 is now to solve for y. So if we add 5 to both sides, we're going to have x plus 5 is equal to y squared. And then to get y by itself, we can use square root on both sides. And because we use the square root to solve an equation, we have to have plus or minus the square root of x plus 5. Now, just going in a little deeper into this problem, technically this is not a function. So when we place a value in for x, let's say 4, 4 plus 5 is 9, square root of 9 is now plus or minus 3. So we have one input, gives us two different outputs. The reason I'm bringing this up is um, the last step of finding an inverse function is to use inverse notation, but it would be incorrect to call this, to use this notation on this expression here because it's not a function. So two things could either state here, inverse is not a function, and just leave it at that, or, and the question didn't ask us to do this, but again, just going a little deeper into this problem, starting before even finding the inverse, we could determine first if the function is one-to-one. Remember, a one-to-one function means it passes the horizontal line test. X squared minus 5 is a parabola. Parabola would obviously not pass the horizontal line test, therefore it's not one-to-one. So this function f right now means its inverse is not a function. So we have an inverse here, but it's a relation, it's not a function. So if we wanted to find the inverse function, which is what this is technically asking us to do, find the inverse function, first what we would need to do is restrict to the domain of part A. Or this domain restriction. So x squared minus 5 just means the parabola has moved down 5 units, so the vertex is at 0, 5. If the domain is restricted to 0 to infinity, what this means is the right side of the parabola. Well, if this is the domain, then this becomes the range. So the output values, if this is the domain of the original function, this becomes the output or the range of the inverse. Meaning we only want positive values then. If the output is going to be values from 0 to infinity, that means we need positive values. So another thing we could do is say, well, if we're only going to have positive values, we don't need the plus or minus, then we just need positive square root of x plus 5. That is now a function. And we could say this then is the inverse function of f. So technically speaking, if they wanted us to find the inverse function of f, then we need to make sure that the original function f is a one-to-one function. In this case, it was not. So we needed to restrict the domain to make it a one-to-one function. Okay, part B. Now we have cube root of x minus 2 plus 1. This is 1-to-1, the cube root graph looks something like that. Passes the horizontal line test. So we don't need to restrict the domain on this one. So we just need to switch the place of x and y and then solve for y. So we can say that x is equal to cube root of y minus 2 plus 1. And now we solve for y. So we're going to subtract 1 on both sides. Now we need to get rid of this cube root here, so we can use an exponent of 3 on both sides. So x minus 1 is going to have a parenthesis, and then it's going to be raised to the third power. And then finally, we can add the 2 to the side. And this is equal to the inverse function of f. Now part C starts the same way. We're going to switch the place of x and y here. And now we have an equation here with a fraction. We need to solve for y. So what we've done with almost all of the equations we're solving with fractions is multiply both sides by the denominator. So if I multiply here by y minus 1 and multiply here by y minus 1, we're going to have y minus 1 multiplied by x is equal to 2. Now we can divide by x on both sides. We're going to have y minus 1 is equal to 2 divided by x. And finally, we can add the 1 to both sides and get y is equal to 2 divided by x plus 1. And this is equal to the inverse function of f. Okay, question 2. This is also from Unit 1. We're graphing functions using transformations. So what's helpful in a question like this is to be familiar with the shape of the parent function. So for part A, for example, the parent function is x squared. If we take away all of these transformations, then what remains is the parent function x squared. That's a parabola with the vertex at 0, 0. So what we then need to decide is if the vertex of the parent function is 0, 0, where has the vertex moved under these transformations? It's 1 unit to the left, 1 unit down. So there's the vertex. Now we need 2 other points. For problems like this on a final exam, the requirement is at least 3 points on the graph. So now that we have the location of the vertex, 1 unit to the left, 1 unit down, we need to find 2 other points on either side to have the correct width of the parabola. So one thing we can do is just plug in x values on either side of this vertex. So like x equals 0 or x equals positive 1. I'm going to plug in x equals positive 1. 1 plus 1 is 2. 2 squared is 4. Half of 4 is 2. 2 minus 1 is 1. So when I plug in x equals 1, I get y equals 1. And then that can be reflected on the other side of the parabola. So that's part A. For part B, this parent function is absolute value of x. Absolute value of x is a v-shaped graph where the vertex again is at 0, 0. So I need to figure out what these transformations, this is 2 units to the right and 3 units up. So the vertex is 2 to the right, 3 units up. And then we have a reflection. This is a vertical reflection. And then the coefficient in front of the absolute value is just 1. So on either side of a vertex, we're just going down 1 and over 1. Like that. For part C, here we have a parent function of just square root of x, and then we have a vertical translation up 1 unit. So the square root of x has a beginning point at 0, 0, and it points up and to the right. Now this vertical transformation here is up 1 unit, so the starting point is 0, 1. And then we need to plug in some x values. So I'm going to plug in x equals 1. The square root of 1 is 1. 1 plus 1 is 2, so 1 comma 2. And then if I plug in x equals 4, the square root of 4 is 2. 2 plus 1 is 3, so 4 comma 3. Question 3, this is also from Unit 1. We have the combination of functions. This is composition of two functions, and this is multiplying two functions. So just be aware of the difference in notation. Open circle is composition. This is g composed of f, or g of f of 5. This is f times g of 4. So for part A, this is g of f of 5. So the input of 5 is only the input for the f function. So the first thing they're going to do is find f of 5. F of 5 here is 2 times 5 is 10. 10 minus 1 is 9. So f of 5 is equal to 9. So this input here, f of 5, is equal to 9. So I can replace f of 5 inside the g function with 9. So now we need to find g of 9. And the square root of 9 is equal to 3. For part B, f times g of 4 is f of 4 multiplied by g of 4. So we have 4 as an input into both functions, and then we multiply. So f of 4, 2 times 4 is 8. 8 minus 1 is 7. And here we have the square root of 4, which is 2. And then we have 7 times 2, which is 14. Okay, question 4. Now this is in Unit 2, finding the zeros of a polynomial. Part A is the rational zeros theorem. This is the p divided by q. So remember, factors for p are factors of the constant value, and factors for q are factors of the leading coefficient. So the factors for p will be the factors of 30. So that's plus minus 1, plus minus 2, plus minus 3, plus minus 5, plus minus 6. Let's see, this is going to be plus or minus 10, plus minus 15, and plus or minus 30. Now, the factors of q are just plus or minus 1. So if we divide all of these values by plus or minus 1, it's not going to change the value of any of these. So this is going to become my p divided by q list right here. These are all the possible rational zeros for part A. Now for part B, to find the zeros, if you recall from Unit 2, we had to just choose numbers from this list at random and use synthetic division until we find a 0, or find a number that gives us a remainder of 0. So typically what happens is most students will start with the lower value here, like positive 1 or negative 1. So if I start with 1, and then make sure that all of the terms in this polynomial are represented, so I don't have to have any zeros for synthetic division. So we just use the coefficients. And it looks like +1 is not one of the zeros. So then start over with a different one. So again, just to save time, just because I know what the solutions are, if you went through a few more like -1, that wouldn't have worked. Um, I know +2 does. So we go to +2, and we have a remainder of 0. So what this tells us is +2 is a 0 of polynomial p. We also know that this set of numbers right here are the coefficients of a reduced polynomial. We started with an x to the fourth, so these are the coefficients of a reduced polynomial of x to the third plus 5x squared plus 11x plus 15. So that's one of the factors, and the other factor is x minus 2. So there's 3 more zeros to find from this factor because it's an x to the third. So we've already ruled out +1 or -1. We know the +2 works. So there's more zeros to find. I'm going to skip to -3 and use the coefficients from this reduced polynomial. So now we have the coefficients. This set of numbers is the coefficients of another reduced polynomial is 1 degree less than x to the third. So since we have a remainder of 0, we know that -3 is a 0 of the polynomial, and that from this set of 3 numbers here, x squared plus 2x plus 5 is a factor. We know that x plus 3 is a factor, and we already knew that x minus 2 was a factor. So we actually have 1, 2, 3 factors for the polynomial. Now we need to decide from this quadratic factor if it can continue to factor into 2 smaller linear factors, or if we need to use a quadratic formula, because there's still 2 more zeros to find. The fundamental theorem of algebra, remember, states that the degree of the polynomial, in this case, this is a fourth degree, the degree of the polynomial is equal to the number of total zeros, real and complex, of the polynomial. So we still need to find 2 more. They're going to come from this factor because it's quadratic. So we are going to have 2 zeros. We just need to decide if we can factor or if we have to use a quadratic formula. There's those 2 numbers that multiply to 5 that also add to 2. So unfortunately, we are going to have to use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So inside the parenthesis here, we have 4 minus 4 times 1 times 5. So 4 times 1 times 5 is 20. 4 subtract 20 is -16. So this is -2 plus or minus the square root of 4i divided by 2. And then both of these values here are divisible by 2. So this becomes -1, that becomes +2. So we have -1 plus or minus 2i. So for part B, the zeros are x equals 2, x equals -3, and x equals -1 plus or minus 2i. And then for part C, which is to factor the polynomial into linear and irreducible quadratic factors, we actually have that done right here. This is the answer for part C. We have linear factors and an irreducible quadratic factor. So for part C, the polynomial p of x is x minus 2, x plus 3, and x squared plus 2x plus 5. Okay, for question 5, this is from also Unit 2. We're sketching the graph of a polynomial function. So the way this was instructed in class is basically to break it down into 3 parts. We need to know the zeros. Let me try that in a different size font. We need to know the zeros. Those are the x-intercepts. The x-intercepts are going to come direct from the factors here. It's already in factored form. So we're going to have a 0 of x equals -1. We're going to have a 0 of x equals 1. This has a multiplicity of 2. So x equals 1. This one has a multiplicity of 2. Remember, that means that it bounces. Anything with an even multiplicity bounces. And then this is x equals -2. Now, x equals -1 here and x equals -2 have multiplicity of 1. That's an odd multiplicity. Anything with an odd multiplicity crosses through the x-axis. So we have zeros at -1, +1, and -2. Now we need the y-intercept. This is when x is equal to 0. So if we plug a 0 in for x, 0 plus 1 is 1. 0 minus 1 is -1, but -1 squared is 1. So we have 1 times 1. Here we have 0 plus 2, which is 2. So we have 1 times 1 times 2, which is 2. So the y-intercept is 2. Now the degree of the polynomial determines the end behavior. And the way I like to sketch just a quick sketch of the end behavior before transferring it over to the main graph. So the degree is when it's in factored form like this, the degree is the total multiplicity. So this is multiplicity 1, multiplicity 2, multiplicity 1. So the total multiplicity is 4. That means it's a degree 4. Any even degree, remember, means the end behavior, the left side and the right side, are going to the same infinity, whether it's positive infinity or negative infinity. Since we have a positive leading coefficient of 1, then both ends of the graph are going to positive infinity. So we have left side is going up, right side is going up. So as we transfer here over to the graph, at this x-intercept of -2, it crosses through, it has odd multiplicity. And it turns up to that x-intercept, which is -1, it also crosses through at -1, comes up there to the y-intercept, comes down here. Now at x equals +1, it has a multiplicity of 2. That means it bounces off the x-axis. Goes back up here, meets up with that other end behavior. Question 6, still from Unit 2. This is from Chapter 3 of Unit 2. We're not actually sketching any graphs. All they're asking us to do is to find the asymptotes and any holes of these rational functions. So for part A, the horizontal asymptote, remember the horizontal asymptote is determined by comparing the degree of the numerator to the degree of the denominator. So this is degree 1, this is degree 1, these are the same degree. If the degrees of the numerator and denominator are the same, then you take the ratio or the fraction of the leading coefficient. So here we have a 1, here we have a 1. 1 divided by 1 is 1. So the horizontal asymptote is y equals 1. The vertical asymptote is determined by the zeros in the denominator. So x equals 4 means we have a vertical asymptote of x equals 4. For part B, we first need to consider the factored form. So the last part of chapter 3, this would have been in section 3.3, we talked about a hole in the graph rather than a vertical asymptote. So typically, if there's two factors in the denominator, that would result in two domain restrictions. X cannot equal -4, X cannot equal -2. However, this one's unique because this factor is the same as this factor. So the x plus 2 factors cancel out, leaving 1 over x plus 4. So now we determine um, vertical asymptote, horizontal asymptote. This one's actually also going to have a hole in the graph. This is when you have a factor in the denominator that's removed because it cancels out or factors out. That produces a hole in the graph rather than a vertical asymptote. So I'm actually going to notate that first. There's a hole at x equals -2. So to actually find where that hole is on the graph, it's at x equals -2. And then if we place -2 into this function here, the simplified version, -2 plus 4 is 2. 1 divided by 2 is 2. So it's at the point, or sorry, it's at 1/2. So it's at the point -2 comma 1/2. Now the horizontal asymptote, here we have a degree 1 in the denominator. The numerator has no variable, it's just a constant value. That's considered degree 0. Anything with no variable is degree 0. So this is degree 0 up here, the denominator is degree 1. The numerator has a smaller degree. That means the horizontal asymptote is the line y equals 0. The vertical asymptote is the domain restriction from the remaining factor that was not canceled out of x equals -4. Now part C, we have a difference now. The numerator has a higher degree than the denominator. So there's no horizontal asymptote. If the numerator has a higher degree than the denominator, remember there's no horizontal asymptote. A slant asymptote, they ask about a slant asymptote in the directions. A slant asymptote only occurs if the numerator degree is higher than the denominator by 1 degree. So if this is degree 2 and this is degree 1, that will result in a slant asymptote. If the numerator is higher by more than 1 degree than the denominator, there's no horizontal asymptote and there's no slant asymptote. In this case, there is a slant asymptote. So if you recall, there was one homework question in section 3.3 where we need to define a horizontal or a slanted asymptote. The way that's done is to divide the numerator by the denominator. So the numerator divided by the denominator. Now, obviously, since the numerator is a degree 1, or the denominator rather is degree 1, we could use synthetic division. However, it's not always going to be the case. So I'm just going to show um, polynomial long division. X goes into x squared, x times x times x is x squared, x times 4 is 4x. So this is x squared plus 4x. We subtract, first terms cancel. 3x minus 4x is -1x. And then we add 2. Now x goes into the negative x, -1 times. Now -1 times x plus 4 is -x minus 4. Now we subtract. This becomes positive, so that cancels out. This becomes +4, so 2 plus 4 is 6. The slant asymptote is the result. It's the quotient right up there, x minus 1. So for part C, I'm going to move this Don't look like I can, so it's all right. Part C, the slant asymptote, is the line y equals x minus 1. The vertical asymptote is still the domain restriction for the denominator. It's x equals -4. Now, one thing that I guess would have been helpful to check beforehand is, would this have canceled with any factors in the numerator? X squared plus 3x plus 2. This factors into x plus 2 times x plus 1. So none of those factors would have canceled out with this making a hole in the graph. So always make sure to consider the factored form. I knew that none of these would factor out. That's why I didn't show the factored form, but just be aware you should always factor and make sure that nothing cancels. Okay, we have two functions to graph, and then we have to answer a series of questions also. So we're going to graph 3 to the x plus 1 power minus 1, but also graph log base 2 of x minus 1 over here for g of x. So let's start with f of x over here. This is an exponential function, so we need to find the y-intercept. So for part A, I'm going to make a quick table of values. The y-intercept happens when x is equal to 0. So 3, if we plug it at 0, this is 3 to the first power, which is 3. 3 minus 1 is 2. So 0 comma 2. Now I'm going to plug in x equals 1. 1 plus 1 is 2. 3 squared is 9. 9 minus 1 is 8. So 1 comma 8. I'm also going to plug in -1. -1 plus 1 is 0. 3 to the 0 power is 1. 1 subtract 1 is 0. We also need, for part B, so this is the answer to part A. Part A is 0 comma 2. That's the y-intercept. The x-intercept is here. Now, the asymptote for a exponential function, remember the asymptote is horizontal. Usually it's here at 0 comma at y equals 0. But we have a vertical translation down 1 unit. So the horizontal asymptote is the line y equals -1. And there are our 3 points here. So we have the y-intercept, the x-intercept, and we have the horizontal asymptote. Now for the second graph, g of x, this is a logarithmic function. Logarithm functions, remember, have a vertical asymptote, usually here at x equals 0, unless there's been a horizontal transformation. X minus 1 is a horizontal transformation 1 unit to the right. So we have a vertical asymptote at x equals 1. The graph is going to be on the right side, so that means we're not going to have any um, y-intercept. We do have an x-intercept. We will have an x-intercept. That's when y is equal to 0. So I'm going to make, again, a table of values. Now we need to strategically place values in for x so that we can easily take log base 2. So these need to be powers of 2. For example, if x is equal to 3, then 3 minus 1 is 2. Log base 2 of 2 is equal to 1. So 3 comma 1. Now we can also plug in x equals 2. 2 comma 1 is 1. and the log base 2 of 1. The log base anything of 1 is equal to 0. So if we plug in x equals 2, we get a 0 out of that. So 2 comma 0, there's our x-intercept. Now one more, log base 2 means I want to have another multiple of 2, or a power of 2 rather. Power of 2 would be, the next power of 2 is 4, so I want a 5 in here for x. Because 5 minus 1 is 4, the log base 2 of 4 is equal to 2. So 5 comma 2, here we have the x-intercept of 2 comma 0. Okay, question 8. We have two logarithm functions, or equations rather, to solve. So for part A, we have to use the product rule. We have to combine two logarithms into one logarithm using the product rule because there's a plus sign between them. We can combine here into the product of x times x minus 3. Now that we have one logarithm, we can use a base to cancel the logarithm. So this is log base 10, the common log. So I can use a base 10 on both sides to get x times x minus 3 is equal to 10. Now we do need to turn this into a quadratic expression. X squared minus 3x equals 10. Now we can subtract 10. And then we can factor into x minus 5 and x plus 2. And we can claim that x is equal to 5 and x is equal to negative 2. Now the problem here is negative 2 in here, in the original version of the equation, you can't have a negative input into a logarithm, or you can't have a value that makes the logarithm negative. So negative 2 is an extraneous solution. 5 works here. 5 minus 3 is 2, so it works there. So x equals 5 is the only valid solution from part A. In part B, it's going to be similar in that we have to combine the two logarithms into one. But now since there's a subtract between the two logarithms, we have to use the quotient rule. So if we combine these into one logarithm, base 6, we form a quotient with a numerator and a denominator. And then we can use base 6 to cancel the logarithm. So this leaves the rational expression. Now, again, we have an equation with a fraction in it. We don't typically leave the fraction in there when we're trying to solve the equation. So we can multiply both sides by x minus 1. If I multiply by an x minus 1 here and then multiply by an x minus 1 there, we're going to get x squared plus 2 equals 6 times x minus 1. Then we can distribute the 6 and get x squared plus 2, 6x minus 6. Now we want to get 0 on the right side, so moving 6x and the negative 6 to the left side, we're going to get x squared minus 6x plus 8 equals 0. And then we can factor into x minus 4 and x minus 2. So then we have now at least two possible solutions, x equals 4 or x equals 2. We need to make sure that none of those are extraneous. 4 squared plus 2, that works. That's positive. 4 minus 1 is positive. So those are good. 2 squared plus 2 is positive. 2 minus 1 is positive. They both seem to check out. Question 9, we have money being deposited into an account. Key word here is compounded continuously. So there's two functions to choose from, but Continuously compounding interest only uses base e exponential. So remember, a of t is a future value at time t, p is the principal investment, r is the interest rate, t is time. So what they're asking for is how long will it take? We need to solve this for time, meaning we had to have an initial amount, which is 10,000, a future amount, which is double 10,000, so that's 20,000, and we have an interest rate of 0.05. So we have 20,000 equals the initial investment of 10,000 times e to the 0.05 t. So divide by 10,000 on both sides. And then to cancel the base e here, we need to use natural log on both sides. And then divide by 0.05. Will give us the approximate value for t. And that's 13.86 years. Question 10. This is from chapter 6, solving systems of equations. This was unit 4. So it says we can use either elimination or substitution. So I'm going to use elimination method. I can see right off the bat that negative 2y, positive 2y, the y's would cancel just by using the top two equations. So I'm going to use the top two equations. So now I'm going to repeat this with two other equations. And remember, you do need to eliminate the exact same variable. So now I'm going to choose the top and bottom equation. So the top equation, the bottom equation. Now we combine these two equations. So the result from step one was this equation in terms of x and z. This result from step two was this equation in terms, whoops, that should actually be z, not a y. There we go. So if I combine those, so now z is going to cancel. We have 6x is equal to 18. So x is equal to 3. So what we have here is a system of equations with a unique solution. We can find y and z now. The other options, remember though, that could happen is at this point, we could have ended up with like 0 equals 3 or 0 equals 10 or something that's not a true statement. That would have been no solution. We also could have ended up here with a statement of 0 is equal to 0. That's infinitely many solutions. If that's the case, you represent the solutions in terms of a parameter z. This one, though, has a unique solution. So now we need to find the value of z. So if x is equal to 3, we can go back to here, for example, 2 times 3 is 6. If we subtract 6 from 14, we get 8. 2z is equal to 8, which means that z is equal to 4. And then if we take one of the original equations, we know that x is equal to 3. We don't know why. Z is equal to 4, so 3 times 4 is 12. So 3 plus 12 is 15. If we subtract 15 from 1, we get negative 14. So we have y is equal to 7. So x is 3, y is 7, z is equal to 4. Question 11, this is the final lesson of the unit. It was 6.7, final lesson of the course, section 6.7, partial fraction decomposition. So for part A, we're going to factor the denominator. Since there's two factors, there's going to be two partial fractions. Now we're going to multiply both sides of this equation by the common denominator. This is the common denominator. So if both sides, the whole thing is multiplied by x plus 3 times x minus 2, when it's multiplied to the left side of this equation, then we're just left with the numerator 6x minus 7. When we multiply the common denominator to the a partial fraction, the x plus 3 cancels out. So a multiplies with x minus 2. Now, when this least common denominator multiplies the b partial fraction, x minus 2 cancels out. So b multiplies with x plus 3. Now, I'm going to use the method described in class that I described as using convenient values for x. We're going to have two convenient values, so I'm going to split this down the middle. First one would be to let x equal 2 here, because 2 subtract 2 is 0, meaning a disappears. So 12, 6 times 2 is 12, minus 7 is 5. A is gone, so we have 2 plus 3 is 5. 5 times b is 5b, therefore b equals 1. Now we're just going to repeat this process with the next convenient value, which here would be negative 3. So let's let x equal negative 3. 6 times negative 3, negative 18. Subtract 7, negative 25. Here we have negative 3 minus 2. That's negative 5a. Therefore, a is equal to 5. So the a value goes with the x plus 3 denominator. So this is 5 over x plus 3. And the b value goes with the x minus 2 denominator. And those are the two partial fractions. For part B, we have a combination of a linear factor and an irreducible quadratic factor. So there's nothing to factor in the denominator because x plus 2 obviously is already factored, and x squared plus 3 is irreducible. So we only have two factors, which means we're going to have two partial fractions. One of the denominators is x plus 2, the other one is x squared plus 3. With linear factors, the numerator is always a single value like a or b or c. With an irreducible quadratic factor, the numerator is a linear expression, like linear meaning y equals mx plus b. So we have a slope and a y-intercept, mx plus b. So we've already used a, so I'm going to start then with b. This becomes bx plus c. That's a linear expression. So again, whenever your denominator in a partial fraction is an irreducible quadratic, your numerator needs to be a linear expression in slope-intercept form. Now we're going to do the same thing we did up above. We're going to take this entire equation and multiply it by the common denominator, which is x plus 2 times x squared plus 3. Now, when this multiplies to the left side of the equation, we're just left with the numerator. When we multiply it to the a partial fraction, the x plus 2's are going to cancel. So this is a times x squared plus 3. Now, when this multiplies the b, x plus c, this partial fraction, the x squared plus 3's cancel out. So we have the bx plus c that's going to multiply with x plus 2. So a little tiny bit different now in how we proceed with this one, since we have this irreducible quadratic expression. We still have at least one convenient value for x, and that's x equals -2. We have -2 squared is 4, times 4 is 16, 5 times -2 is -10. So 16 plus -10 is 6, 6 plus 8 is 14. Here, -2 squared is 4, plus 3 is 7, 7 times a is 7a, and here, -2 plus 2 is 0, so this whole side of the equation is gone. So we have a is equal to 2. Now we do not have any more convenient values. There's nothing I can plug in for x here that's going to make this equal to 0. So we can just plug in a random number like x equals 0. Remember though, when you use random numbers for x, you have to plug in anything that you've solved up until that point, which is a equals 2. So x equal to 0 is 0 plus 0 plus 8, which is 8. Here we have 0 squared plus 3, which is 3, and then a is equal to 2. 3 times 2 is 6. X is 0. So 0 times b is 0. 0 plus c is c. So this is c times x is 0 plus 2 is 2. So this is c times 2, which is 2c. So then if we subtract 6 on both sides, we get 2 is equal to 2c. So c is equal to 1. We're almost there. Now we just need to find the value for b. So again, we're going to plug in just a random number for x, like say x equal to 1. But now we have to plug in a is equal to 2 and the c is equal to 1. So if x is equal to 1, we have 4 plus 5, which is 9. 9 plus 8 is 17. Let's see, we've got x equals 1. So 1 squared is 1 plus 3 is 4. And then a is 2. So 4 times 2 is 8. We have x is 1. 1 times b is b. C is 1. So this is b plus 1 in parentheses. And then here we have 1 plus 2. So this is 3. So 3 is going to distribute to b plus 1. So that's 3b plus 3. So if we subtract 8, we're going to get 9. If we subtract 9, we're going to get 6. 3b, so therefore b is equal to 2. So a, you can see, is equal to 2. So this is 2 over x plus 2. And then bx plus c, b is 2 and c is 1. So this is 2x plus 1 over x squared plus 3. Okay, question 12, inverse of a matrix. This is section 6.6. So for part A, first need to create the matrix equation. Now, we have not been given the inverse. We need to multiply both sides of this matrix equation by the inverse of this coefficient matrix, because that's going to cancel this matrix leaving xy by itself, and then we have to take and multiply it over here by the inverse. So the next step is to find the inverse. The inverse of that matrix is 1 over a times d, so that's negative 20, minus b times c, so that's negative 18. And then we switch the place of a and d, so we have 5 and negative 4, and then b and c change signs, so it's a positive 3 and a negative 6. So this is negative 1/2. Negative 20 plus 18 is negative 2, so negative 1/2. There's this matrix. That's the inverse. So what we need to do then is multiply the inverse here and here. Now, if we multiply this matrix by its inverse, all that's going to happen is it cancels out. Remember, I don't require that you show that, but I do require that you show what happens when you multiply the inverse there. The last part of part A would be to take the inverse and multiply it with the matrix on the right side of the equation. So this entry that's in row 1, column 1, we need row 1, column 1. So this is 5 times negative 4, it's negative 20, plus 3 times 8, it's 24. So negative 20 plus 24 is 4. Now for row 2, column 1, we need row 2, column 1. So negative 6 times negative 4, that's 24. And then negative 4 times 8 is negative 32. So 24 plus negative 32 is negative 8. And then we need to take this negative 1/2. So negative 1/2 times 4 is negative 2. And negative 1/2 times negative 8 is positive 4. That's equal to x comma y. So the solution is negative 2 comma 4 for part A. For part B, we need the matrix equation. And it gives us the inverse already in part B, which is nice. We don't have to find the inverse of a 3 by 3 matrix because that takes a long time. So the coefficient matrix is actually given to us right here. This is A is equal to the coefficient matrix. So we have and then the variables are x, y, and z. That's equal to negative 12, negative 10, and 6. We already know the inverse. It's given to us here. So um, we can skip this whole part of finding the inverse. Now we just need to show the inverse multiplied by this matrix here. So the inverse multiplied by this matrix. So row 1, column 1 is row 1, column 1. Negative, or 1 times negative 12 is negative 12. 0 times negative 10 is 0. And then 2 times 6 is 12. So we have negative 12 plus 12. With row 2, column 1, we have row 2, column 1. So 1 times negative 12 is negative 12. Negative 1/2 of negative 10 is 5. So we have negative 12 plus 5, which is negative 7. And then we have 3/2 times 6. So that's 18 divided by 2. That's 9. So we have -7 plus 9, which is 2. Then we have row 3, column 1. So this is -12 plus 5. That's -7 plus half of 3, or half of 6, which is 3. -7 plus 3 is -4. So the solution is 0, comma 2, comma -4. Okay, question 13. We have Cramer's rule to solve for only one variable, it's y, in the following system of equations. So we need to find the d determinant, and we need to find the d sub y determinant. Now, the d determinant is just the matrix of coefficients. So I'm going to use the method where we just copy the columns to the right side. So, so here we got 1 times -1 times -1. That is 1. Here we're going to get 1 times -2 times 1, which is -2. Here we have 1 times 2 times -2. That's -4. Now in the other direction, 1 times -1 times 1 is -1. -2 times -2 times 1 is 4. And -1 times 2 times 1 is -2. So in this direction we add, in this direction we subtract. So this is 1 plus -2 plus -4, and then we subtract -1, subtract 4, subtract -2. So this is 1 minus 2. It's -1 minus 4 is -5, plus 1 minus 4 plus 2. So this is -4 minus 4 is -8, plus 2, -6. Now for d sub y, the y column, which is the middle column, gets replaced with those constant values of 4, -1, +1, and everything else stays the same. Again, just for consistency, I'm just going to use the same method of copying the first two columns over to the right side. And this cross, so 1 times -1 times -1 is 1. 4 times -2 times 1 is -8. And then 1 times 2 times 1 is 2. Then in this direction, 1 times -1 times 1 is -1. 1 times -2 times 1 is -2. And -1 times 2 times 4 is -8. The bottom numbers there are going to add 1 plus -8. Let's do this. Ones in blue we're going to subtract. So 1 plus -8 is -7. -7 plus 2 is -5. Plus 1 plus 2. -5 plus 1 is -4. -4 plus 2 is -2. -2 plus 8 is 6. So then y is equal to d sub y divided by d. So d sub y is +6. D was -6. We have y is equal to -1. Question 14. This is from Unit 3, actually, when we were doing the unit of exponential functions and logarithmic functions. There were a few sections from chapter 7 that were sequences and series. So a series is adding certain numbers in a sequence together. So um, in question 14, we have a series, meaning we have 15 seats in the first row, 17 seats in the next row, 19 in the third row, 21, and then it adds and adds and adds. It doesn't add forever. This is not an infinite sum. There's 20 rows of seats, so we need to know what the number is in the 20th row. So when n equals 1, there was 15 seeds. When n equals 2, there were 17, and so on, n equals 3. So since we're going up by 2 every time, this is an arithmetic sequence. You will have the formula sheet, which will give you the um, explicit formula for an arithmetic sequence. It's a sub 1 plus n minus 1 multiplied by the common difference. So we have 15 as the first term, n minus 1 times the common difference. The common difference is 2. This is 2n. This is 2n minus 2. Minus 2 combined with 15 is 13. So this is 2n plus 13. So then the 20th term, a sub 20, is 2 times 20, which is 40. And then 40 plus 13 is 53. So there's 53 seats in the 20th row. So now we have to add this all together. So the other formula you will have on the formula sheet is the partial sum of an arithmetic sequence. So if we're going from the first to the 20th spot of 2n plus 13, then the partial sum is n over 2 plus times the first term plus the last term. This is the partial sum of an arithmetic sequence. N is the number of terms being added, so that's 20. The first term is 15 in the sequence. The last term in the sequence was 53. This is 10. And then 53 plus 15 is 68. So this is 680 seats. And then question 15 here, we have an arithmetic sequence with two of the terms. We know the 14th term and the 25th term. So one way we can think about this is in a table form. We have n, which is the spot that the number is in, and then a sub n is the actual number in that spot. So the 14th term is 72, and the 25th term is 127. So since this is an arithmetic sequence, we know that that means there's a common difference. And if you recall from chapter 7, which was in unit 3, a common difference is like a constant rate of change, a slope. A slope is the difference in y values divided by the difference in x values. So the difference in our term values, a sub n, is 127. 127 minus 72. So that difference is 55. And then the difference in term values is 25 minus 14. So meaning the number of terms. So from the 14th term to the 25th term is 11 terms. So in the span of 11 terms, we increased by 55. So 72 went to 127. So the difference in y values is 55. In x values, it's 11. So 55 divided by 11 is 5. That's equal to the common difference of this arithmetic sequence. So the explicit formula for the arithmetic sequence is, again, a sub n is equal to the first term plus n minus 1 times the common difference. We don't know the first term, but we do know the common difference is 5. And we know for an n value of 14, for example, we have an a sub n value of 72. So we can plug those in. A sub n is 72. We don't know the first term. The n value for 72 was 14 minus 1 times 5. So 14 minus 1 is 13. And then 13 times 5 is 65. If we subtract 65 from 72, we get 7.